Okay, so I would like to give a brief introduction to these additional homework problems from sections 1.5, 1.6, and 1.7. 1.5 talks about orthogonal matrices, which is an important class of matrices. 1.6 talks about eigenvectors and eigenvalues. 1.7 talks about symmetric, positive, definite matrices. So these exercises kind of explore some of the relationships between these types and also goes deeper into some specific examples. Okay, first of all, I'm going to look at a specific example of a type of matrix called or projection matrix. Projection matrix is satisfies this property, p squared equals p. And as we saw in class, p zeroes out some directions and preserves certain directions. Now, one example of a projection matrix is take the identity matrix and cross out some of the diagonal entries. And you will have a projection matrix as you can verify. And in some sense, that's almost the most general case. All right, now, so the exercises are as follows. Show that every vector in the column space of P is an eigenvector of P with eigenvalue 1. All right, I think you should know how to do that. You need to write down an equation and verify that the column vectors satisfy that equation. And what's more, any vector in the column space satisfies this equation. It's not just the column vectors, the columns themselves, but the column space. Every vector in the column space is an eigenvector. Okay. Number 2, show that every vector in the null space of P is an eigenvector of P with eigenvalue 0. All right, so we've got these two things. Okay, number 3, show that if P is of size n by n, then P has n linearly independent eigenvectors. Now these may or may not be unique, but I can choose n linearly independent eigenvectors. Now what eigenvalues do they have? Well, some have 1, some have 0. But I'm not specifying that in this problem. You just want to show that P has n linearly independent eigenvectors. So a way to approach this is show how you would construct linearly independent eigenvectors from using this information here. All right. Now show that the n linearly independent eigenvectors can be chosen so that they are orthonormal. That means orthogonal and have length 1. Okay. So not just so this just means that the basis of the what you call the eigenspace, the basis of the set of eigenvectors has an orthonormal basis. I didn't say that quite right. The set of linearly independent eigenvectors has an orthonormal basis, a set of vectors that spans the set of eigenvectors, and all the vectors are orthogonal and have unit length. Unit length, as I hope you know, is that means that the norm squared is equal to 1. All right, it doesn't show, but the norm squared equal to 1. Okay. All right, it's not behaving for me. Let's do this. Norm squared equal 1. How about that? Okay. All right, now show that P is a projection if and only if A, 1 is the only non-zero eigenvalue of P, and B, P is diagonalizable. That is, P can be written as Q, D, Q transpose, where D is a diagonal matrix and D is an orthogonal matrix. So I should say that B is diagonalizable with an orthogonal matrix, because sometimes you might have a diagonal where the matrix is not orthogonal. So it's diagonalizable with an orthogonal matrix. Right? Remember that Q is orthogonal means that Q transpose equals Q inverse. Right? So let me just add that too. Whoops, I don't know what the transpose of Q is Q inverse. Okay. All right. Number 6. For any n by n matrix A and any vector V in Rn, all right, so this V is in the, so A can be applied to V, right? You can multiply A by V because it's the right size. Okay. So we may write V is equal to AV plus I minus A times V. So why is that? Just work this out. Use the associative law, this distributive law, and see how the terms work out. Show that I minus A is a projection if and only if A is a projection. There should be if and only if, not if and only of. If and only if A is a projection. Okay. So if I've got one projection, I've got two. Okay. Now if P is a projection, show the column space of P is orthogonal to the column space of I minus P. Now this is why projections are sometimes called orthogonal projections, because that means that this vector here is in the column space of AV. This vector here is in the column space of I minus AV. So if these two are orthogonal, that means I've split V into two orthogonal parts. All right, so that's why P is called an orthogonal projection. Right now, a rank 1 matrix A can always be written as A equals WV transpose. If A represents a one-dimensional orthogonal projection, then what can be said about W and V? What is the geometrical significance of these vectors? Okay. All right, so this is kind of an exploratory question, but you might think about what this says in terms of eigenvectors. Okay, think about how W and V relate to the eigenvectors of A. That's a good way to look at this. Okay, because eigenvectors give you a lot of information about the matrix A. Okay, you could also consider the null space of A. I mean, are these vectors in the null space? Are these vectors? So think about those questions. All right, see how far you can get and saying what you can say about W and V. Okay, number 9, show that if P is an orthogonal projection, then M equals minus P plus I minus P is an orthogonal matrix. And supposing that M is n by n and the rank of P is R, what are the eigenvalues of M? Is M a rotation or a reflection? Remember, rotation means the determinant is 1, and then the reflection means the determinant is minus 1. All right, so think about that question. Right. All right, let's move on to the next group of questions, and this is relating eigenvalues to differential equations. Eigenvalues are the key to linear differential equations. So I say linear, that's a particular type of differential equation. All linear differential equations can be written in the following form. dv dt, where v is a vector, dv dt equals a times v. So this v is a vector, a is a matrix. A is going to have to be a square matrix because the output is the same size as the input. So a is equal to square matrix. Okay. So one example of this is Newton's law. So I showed in class, I just go over this briefly, I showed in class how you can convert Newton's law into a first order, this is first order because it has one derivative, a first order vector differential equation. So F equals ma, F equals force, m equals mass, a equals acceleration, which is the second derivative of the position. All right, so I rewrote Newton's law in this way. The second derivative of the position with respect to time. So this is second derivative of position with respect to time, which I should say. Okay, so let me just make this clear. F equals force, m equals mass, a equals acceleration, which is the same thing as second derivative of position with respect to time. So here we have Newton's equation, which I've divided by m to get this way. I want to get the derivative by itself, and then I define two variables. I say x1 is the original x, the position, x2 is the velocity. All right. So I know d squared x dt squared, well, that's the derivative of the derivative, so it's d dt of dx dt, which is the same thing as d dt of x2. All right. But remember that, so I have dx1 dt, well, x2 is defined as dx1 dt, and dx2 dt is the second derivative of x2, which is equal to f of xt over m, so that's this here. Okay, and x is the same as x1 and x2, so I have a function of these three variables, x1, x2, and t. So if f is linear in x1 and x2, that is, f is a linear combination of these two variables, then I can write this as d dt of x1, x2 equals this matrix times x1, x2. So I ask you to do the same thing for a different linear differential equation. It's a differential equation of a different size, different order, and I want you to convert that into this same form, dv dt equals av. So you can look this up and find that differential equation. And that's the first problem. All right, now, in this section we talk a little bit about solutions. Okay, actually this should be 2 and 3 because this is the same section. So let me convert this to a 2. And I'll convert this to a 3. Okay, we're good. All right, so now let's consider this equation. Now, if v was a scalar number or a scalar function, then you'd get this solution for your differential equation. X is equal to the initial x times the exponential of a times t. In this case, okay, so in this case, if this capital A, this small a, let me make this a capital A because that's what I'm comparing it to. So let me make this a capital A. All right. So if v was a one-dimensional vector, that is a number, then this would be the solution by basic calculus. Now it turns out the solution for the vector equation, we may have a chance to look at this, why this is true. The solution to the vector equation is v of t equals the exponent of TA times V0. Now, one thing you notice is that I did not write the V on the left-hand side. I did that on purpose. Why is that? Because this is a matrix. I'm multiplying this matrix times a vector. I cannot put the vector on the left-hand side because if I'm choosing V as a column vector, I can't multiply column vector times a matrix. I have to multiply a matrix times a column vector. So this is a new wrinkle. You have to worry about the order in which you write the function and the coefficients. Right? So we've got this situation. Now, if A is a matrix, then the exponential of TA can be defined by power series. This is a power series from calculus, right? This is what you call Taylor series. Okay, and then I'm just doing the same thing with a matrix. I'm plugging in the matrix instead of the number. And this is perfectly well defined because I can multiply matrices together. Right? This is a perfectly well defined matrix. And it turns out that this converges in everything. I'm not going to talk about that, but it turns out this is well defined. It's a well defined power series. All right. Now, if A is diagonalizable, then the power series simplifies tremendously. So number 2 says show that the matrix power series, using the matrix power series above, that the exponential of TA is equal to x times the exponential dt times x inverse. Okay, so this is actually a straightforward problem, but you do need to, would like you to go through the steps, right? Okay, so this is 3 and 4. Sorry, I didn't realize I had even more problems than I thought. Okay, so let's make this 3 and 4. That's 3 and this is 4. Okay. All right, so the eigenvalue of A with the largest absolute value determines the behavior. Okay, so that's what I want to show below. All right, this is what we want to. So, for example, suppose D1 is the largest eigenvalue. And I did this in class. If I take the ratio of these two numbers, which are the two diagonal entries corresponding to the two eigenvalues, when I take this the ratio, I'm going to get this number here. And when t goes to infinity, this gets larger and larger. Okay, sorry. All right. So the diagonal term is much larger than the other terms. All right, so I have two follow-up problems on this. If V1 and V2 are eigenvalues of A with eigenvalues D1 and D2, express V of t equals this function here. Now this is the solution of the differential equation with this initial vector, right? This is, I'm just plugging in this linear combination in for this V0 here. Okay, so I'm taking a specific example of a initial condition of an initial vector. This initial vector is this linear combination of the two eigenvectors. It's this linear combination C1v1 plus C2v2. All right. So I want you to express this in terms of these two. And I want to express it as a linear combination of these two vectors. Okay, this is not a difficult problem. It's not a trick problem, it's not a difficult problem. I'm just setting up the next problem here. Okay, suppose V1 and V2 are, as in the previous problem, have D1 equals 1 and absolute value of D2 less than 1. Find V of 0 and the limit as t goes to infinity of V of t. All right, so that follows on from number 3. Okay, so that's the second section of problems. Let's go on to the third section where we talk about some properties of symmetric positive definite matrices. Okay, so let me just give you a very important example of symmetric positive definite matrices from probability. You have something called a covariance matrix. So I'm not going to go too deeply into the probability, but I'll just give you some taste. Some people may have more or less background in this area. So if you haven't had too much about probability, then just let this pass by. You'll see this again. Okay, so let's take a 2x2 example. Suppose you have two random variables like height and weight. Okay, now these two variables, I think you have some idea, they're correlated. The taller people tend to weigh more, so there's something called the correlation. Now every random variable has a variance. You know that also, that there's a variability in height and variability in weight that's related to the standard deviation. In fact, it's the square of the standard deviation. Now if you have two different random variables, they also have something called a covariance. How much do they vary together? And that's very closely related to correlation. Correlation is always between -1 and 1. Covariance, it can be larger than that. Again, it measures how closely related these two random variables are, how much they vary together. The variances and covariances can be put into a single 2x2 matrix called the Covariance Matrix Sigma. So if you have two random variables, I'm going to label them Z1 and Z2. You can think of Z1 as height and Z2 as weight. It turns out that the variance of x1 z1 plus x2 z2 for any two constants x1 and x2 is equal to the row vector x times sigma times the column vector x. Okay, where x is this vector here. Now I write the semicolon because I use that to denote column vector. You see that notation in a lot of computer languages, including MATLAB and Wolfram Alpha. Okay, so this denotes the column vector x1 on top of x2. Now, since the variance is always positive, it follows that this quantity is greater than 0 for any vector of x. So the covariance matrix is positive definite. It also turns out that the covariance matrix is also symmetric. Single 2 by 2 symmetric matrix. Now, why is it symmetric? It's symmetric because the covariance of z1 and z2 is the same as the covariance of z2 and z1. Okay, so I could say this. Let me just say this: the sigma, the ij entry of this, is equal to the covariance of the two random variables. So I can say z1 and z2. Okay. I'm sorry, zi and zj. Sorry about that. Okay. All right. So, whoops, that's a j. All right. So the covariance of sigma is the covariance of zi and zj. So from here you can see that sigma ij is equal to sigma ji, because the way that the two random variables vary together, it doesn't matter which order you write them in. You're just talking about how much they vary together. All right, now, the book refers to this quantity, x transpose x as the energy, in particular when S is a positive definite matrix. This comes from an application when you have a potential energy function E of x that depends on a vector of variables, i.e. position in 2 or 3 dimensional space. Okay, so if the energy has a local minimum at point x0, then the energy can be approximated as this parabolic function, 1/2 x minus x0 transpose times s times x minus x0 plus E0, and there's no plus here, where E0 is the energy at x0 and s is the matrix of second derivative of E, also called a Hessian. This is like Taylor series. This is like Taylor series in one dimension, but it's extended to higher dimensions. Okay, so let me say a little bit about this. Now, when you think about potential energy is like gravity. Okay, so let me give myself a little more room. Okay, and we can talk about this a little bit. All right. Okay, now the potential energy of gravity is proportional to height. Right. Now, why is that? Well, to climb up the stairs, it takes energy, right? And then if you jump down the stairs, or if you jump off a cliff or you jump off a diving board, by the time you reach the bottom, you have a lot more kinetic energy, a lot more motion energy than you did at the top. Where did that motion energy come from? Well, your potential energy, which you got from going up high, was converted to kinetic energy. So you can think of gravity having potential energy which is the same as height. Now let's think of a contour. Let's think of a bowl or a valley here. Okay. Okay. So you can think of this as a valley. So down here the potential energy is minimized. Okay, and then you have this bowl coming up like this. Now, you may remember from calculus, if you have an equation of something like this is what you might call a paraboloid. And this is a three-dimensional equation, so your height is up here, z is this way, and then you have x and y. Okay, and you could write this as z is some function k times x squared plus y squared. All right. Another way of seeing this is that the height is constant on circles of constant radius. You see, when on a circle of constant radius, x squared plus y squared is constant. As the radius increases, the height gets bigger. So you can see that here. This is a circle. Here's another circle. As the height goes up, these circles get bigger and bigger. And the rate at which the radius gets bigger and bigger, well, it goes as the radius squared. The height goes as the radius squared. Okay. All right. Now I could write this in the following way. I could write this as z equals xy times k xy. Right. This is called a quadratic form. This is a very important transformation that you see all the time in physics and in other applications as well. All right. So here I've written this in the form of the vector x times a matrix S times another vector here. And this matrix is symmetric. All right. So that's what I have here. Now, here I use the fact, when I say x to x squared plus y squared, I'm using the fact that this is the point 0, 0. Now, if this is the point x0, y0, I think I need to leave myself a little more room. Is this going to go? Okay, good. All right. Okay. So let me make my picture a little bit more detailed and add some important things here. If I take this point as x0, y0, all right, this here is an aside here. I mean, that goes with this picture. If this point is x0, y0, then I don't have x squared plus y squared anymore. What I have is, so let me erase this and do this in more detail down below. Oops, sorry, that's not going to wash. Okay, I wonder if I can do this. Nope, that's not going to work. So let's go here. Okay, sorry. Let me just want to erase that last piece so we have something good. All right. Just be patient with me. All right. All right, now in this case, what is my equation here? Well, I've translated the bowl. Okay. All right, so let me be a little bit more specific here. Suppose this point down here is not just x0, y0, but it's x0, y0, e0, where e0 is the height. Okay, this is going to have 3 coordinates because it's in 3 dimensions. So I'm going to say this point is x0, y0, e0. And I say e0 because I'm identifying the height with the energy. So I'm identifying ez with the energy. So I call this x0, y0, e0. So the equation of this bowl is what? Has the form. So I had before x squared plus y squared. I've had z squared equals x squared plus y squared. I have to modify this a little bit. So, okay. All right. Now, how do I have to modify this? Well, look, because it starts at x0, y0, I have to translate so that the 0 point is at x0, y0. Okay. And I have a k to give the steepness. And then I also have plus e0. Okay, because that shifts, that's the vertical shift. Okay, so this is the 0 point. The x0, y0 is the 0 point. And e0 is the vertical shift. And you can see here that what we have is z is equal to, I can write this as x minus x0, right? Because that's the vector here, x minus x0. I'm using the vector x to represent xy. And then here I have k, 0, 0, k. And then here I have x, also the vector x0, x minus x0. And then this should be transposed, right? Okay. All right, now, it turns out that this is a particular example where you have circular cross-sections. You can have elliptical cross-sections, and the ellipses can be rotated in the xy plane. And what that corresponds to is a different matrix here, but that matrix is still always symmetric. All right. So you can see that this whole question is related to ellipses and rotating ellipses. Okay, and when you talk about covariance, you also talk about covariance ellipses, because ellipse kind of gives the shape of the way the symmetric positive definite matrix works. Okay, some directions are different from others, and it turns out that the different directions of the ellipse correspond to the different eigenvectors of the symmetric matrix. All right. So page 51 says any ellipse can be rotated by orthogonal matrix to diagonal form. So here's a diagonal form. It turns out I can rotate. Now rotate, what does, so that's what orthogonal matrix means. It means to rotate a matrix means to do a similarity transformation with an orthogonal matrix. All right. So any ellipse can be rotated by orthogonal matrix to diagonal form. This is also true in higher dimensions. This is called the principal axis theorem. Now, I'm not going to prove, but it's important to get the intuition. You get the intuition in 2 dimensions, and a lot of the same things work for higher dimensions. All right, now, suppose that A is a 2x2 rotation matrix corresponding to a counterclockwise angle theta. Right, so what am I talking about here? You've just got rotation matrix theta. Now, hopefully you know what matrix this is. If you don't know what it is, you can look it up. It's in the book, or you can just Google, I think, rotation matrix for angle theta. Now, we always measure angle counterclockwise, but the matrix has cosines and sines in it. So you can look that up. Now, suppose f is a function from R2 to R. Like this, for instance. This height function is a function from R2 to R. For every point in the plane, I have a height. So this f is one example of a function from R2 to R. And this function is not necessarily linear. So what's the geometrical relationship between the graphs of f equals c and f of ax equals c? All right. And here's an example here. F equals c is one of these circles. Now, if you circle and you rotate it, of course, you're still going to get a circle. But suppose you have an ellipse. Okay. So the question is, this A geometrically corresponds to a rotation of angle theta. And if I have a graph like this, this could possibly be an ellipse. If I take this graph instead, f of ax equals, say, what's the difference between the graph of this one and the graph of this one? Okay. There should be, and if you don't know, you can do some example. You can try to do some example. Instead of k and k here, you could do 1 and 2, and see what happens when you rotate that. See what happens when you rotate those variables. Okay. All right. So see if you can do that. All right. Okay. So number 2, given the ellipse E with semi-major axis 3 and semi-minor axis 2 along the x2 axis. So what does this mean? I'm talking about the x1 axis here and the x2 axis here. And I'm saying semi-major axis is 3, so it's 3 here. Sorry, it's 3 here, and it's 1 here. It's not helping. Okay, there we go. Nope, it doesn't like it. There we go. Okay, so this is 3, and then this is 1. Okay, and it's centered at 0, 0. Okay, so write the equation of the ellipse as f transpose mx equals 1. Where x is x1 and x2. Okay, semicolon denotes column vector. Okay, so translate this graph here into an equation that looks like this. So I talked about how the relationship between the graph and this matrix form up here. See if you can extend that to this case here, where you have an ellipse instead of a circle. Okay, all right. So in B, find the equation of the ellipse E rotated at an angle pi/4 counterclockwise. So pi/4 counterclockwise when you take this, rotate it this way, so it's up. So it's up this way, right? Okay. Right. So I want an equation for that graph. All right. So here's an ellipse. Now, if you remember, there are different types of conic sections. An ellipse is a conic section. Hyperbola is also a conic section. There's a small difference between the equations. In a ellipse, if you have 2 variables, typically you have x squared plus y squared, or x squared over 4 plus y squared over 9 equals 1. If you put a minus here, then it's a hyperbola. Okay, so here's a hyperbola. You can graph it. This is algebra 2. Find a change of variable y equals ax so that the equation can be written as y1 squared minus y2 squared equals 1. Okay, so here this A is a matrix, right? Okay, see if you can do that. All right, now find the equation of the ellipse y squared minus y2 squared, y1 squared minus y2 squared equals 1, rotated counterclockwise by pi/4 radians. Okay, so this one is related to this one here. In fact, you can use part B here you can use the same pattern in part B here to solve this part C here. Okay, Okay, then replace y1, y2 in there with their expressions in terms of x1 and x2. All right, so what you've done is you've taken this hyperbola, you've transformed it by change of variable, and then you've rotated it. Now, part B, I say find the equations of the equation of the hyperbola, this hyperbola rotated pi over 4 radians counterclockwise. Okay, so here I'm first doing the rotation, and then I'm doing the rotation. Here I do a change of variable before rotating, then I rotate, and then I go back to my original variables. Here I'm just rotating without changing the variable. So it's actually quite a bit simpler to rotate this one than to rotate this one, right? So, but the question is are they the same? Can I actually change variable first and then rotate and get the same answer if I don't change variable? Okay, so you can explain why or why not these are the same. I mean, you might think that if you multiply something by a number and then divide by the same number, you get the same answer. Now here I'm not doing the change of variable. I'm still rotating. Here I'm rotating. Here I'm rotating. Both rotations are pi over 4. Do I get the same answer if I do this one and I do this one, or are the answers different? Okay. I can say again that here what I'm doing is when I do this change of variable, that's like doing something, and then here when I go back, I'm undoing the same thing. Okay. So the question is, are these two results the same, and and explain why and why not? Okay. All right. So number 4, without doing any calculation, describe the graph of the following equation: x transpose mx equals 1, where I have this matrix here, product of 3 matrices. Explain your reasoning, how you understand what this graph looks like without doing any calculation. So here it's very important that you do the describe and explain your reasoning. How do you know that that's the answer? All right, now consider the rank 1 matrix A equals VW transpose, where V and W are linearly independent column vectors which are not orthogonal, where the non-zero eigenvalues of A. All right, so this is actually related to the question above, where the non-zero eigenvector, there might be some redundancy here, but where the non-zero eigenvectors of A, show that A equals has n minus 1 linearly independent eigenvectors with eigenvalue 0. Prove or disprove A is diagonalizable. Prove or disprove the eigenvectors of A with different eigenvalues are orthogonal. And A is symmetric if and only if V is equal to W. Show that A can be written as A equals Q transpose, where Q transpose equals 1, if and only if A is symmetric. And here in this A, I'm referring to this matrix here. Okay. All right. So there's a sequence of problems here. Okay, that's it. So we'll talk about some of these during class next week, or during our sessions next week. But here's a preview that hopefully can get you jump started.